We're just like using what we got. And that's my plan then. Everybody cool? Okay. Fire away. Right, at this point you guys would have looked over stuff because you probably got to school planning on taking this test today. So if you're don't feel great about things or you're shaky on something, like now's a chance to ask some questions. We do some clarification and maybe feel a little bit better than when we did when we walked in. Absolutely. Do you have something in particular, or you just want me to grab something? Okay. All right. Let's go. I'm going to grab the... Did we do this one last time? We did? Okay. Do we do this one? You don't think so? Yes or no? No? Okay. I heard some mumbling then after. I just want to make sure I'm not wasting anybody's time or whatever. So here's another related rates problem. So it says, ship A is traveling due west towards Lighthouse Rock at a speed of 15 kilometers per hour. Ship B is traveling north away from Lighthouse Rock at a speed of 10 kilometers per hour. Let x be the distance between ship A and Lighthouse Rock at time t, and let y be the distance between ship B and Lighthouse Rock at time t, as shown in the figure above. So I'm going to add in here that we have dx dt and dy dt given to us. So ship A is traveling due west. So should this at 15 kilometers per hour, because we're traveling west, is the length of x getting bigger or smaller? Smaller. So dx dt should be negative. And ship B is traveling due north away from Lighthouse Rock. So should dy dt, or is y getting bigger or smaller then if we're going north? Bigger. So that means dy dt should be positive, right? So I'm going to write that in for myself. Find the distance in kilometers between ship A and ship B when x is 4 and y is 3. Well, that's pretty easy, right? What are we going to do for that? Yeah, I'm going to call that side r, so just 4 squared plus 3 squared equals r squared. So r is 5. No biggie. Find the rate of change in kilometers per hour of the distance between the two ships at x equals 4 kilometers and y equals 3 kilometers. So we're looking then for dr dt, right? So what equation is going to relate to x, y, and r? Pythagorean theorem. And if I do the derivative of both sides with respect to time, we get that, right? So I know that x is 4 and dx dt is negative 15. Y is 3 and dy dt is 10. And then r is 5 and dr dt is what we are searching for. So what do we get there? 6 and then minus 12, so negative 6, I think. You'd have to double check my arithmetic, but you get the idea, right? I think that's it. How did I do it so fast? Right? So negative 12 plus 6. And I guess I should have a unit on that. Okay. Let theta be the angle shown in the figure. Find the rate of change of theta in radians per hour when x is 4 and y is 3. So I need an equation. Okay, so I could use tangent. I could say tan theta equals y over x. Or what else could I do? Yeah, theta equals tan inverse of y over x. Either one will be fine. I kind of like this one because I don't have to do any trig stuff with the triangle. But it's fine if you use the other one. You have to use r as 5 and then use the triangle to do like secant or secant squared of theta. But let's do this. So we'll do the derivative of both sides. What's the derivative of tan inverse? Yeah, but in this case our x is y over x squared. And then that's going to involve using a quotient rule when we do the chain then, right? So we have the bottom times the derivative of the top minus the top times derivative of the bottom all over the bottom squared, right? And now we just kind of plug in. What do we get then? The denominator's 10, and then I have 40 plus 45, so 85. Something like that. Is that feel okay? Sure. You want to do another one? I'm happy to do another one. I think we might have even done that before. Have we done that one before? You don't remember? I don't remember. Let's go look at these guys. Maybe there's a good one of these multiple choice ones at the end are tough. Let's do 11. Feels like a good one. You guys are good doing another, right? This tends to be, probably the hardest skill of the skills, at least from a free response question standpoint. 11 reads, a piece of rubber tubing maintains a cylindrical shape as it is stretched. At the instant the inner radius of the tube is 2 millimeters, the height is 20 millimeters. The inner radius is decreasing at a rate of 0.1 millimeter per second, and the height is increasing at a rate of 3 millimeters per second. Which of the following statements about the volume of the tube is true. For example, it says the volume of the cylinder with radius r and height h is yada, yada, yada. Okay. So important here is it tells us that each of these things is changing, right? That the radius and height are both changing as we're stretching the cylinder. So if I differentiate both sides, I must use the product rule. So I know R is 2, and dH dt is 3. dr dt is negative, because it says decreasing, 0.1, and then h is 20. So 12 minus 8, so I have 4 pi, and that's positive, so we're increasing. Does that feel okay? No? Yes? That's all right? Giselle.
Can we do another file effort, please?
Sure. All right. Let f be a twice differentiable function with f of 1.5 equaling 3. The derivative of f is given by f prime equals yada, yada, yada for 1 to 4. So twice differentiable, what's that mean? So sure, the mean value theorem would apply because we know that if f is differentiable, it's continuous. And if it's differentiable, then the derivative exists. And if it's twice differentiable, the second derivative exists, right? Everybody's cool? Okay. So it says find all the values of x on the interval from 1 to 4 at which f has a critical point. Classify each as the location of a relative maximum, minimum, or neither. Justify your answer. Okay. So I'm going to find critical values. What are the two things we need to look for? Where the derivative is 0 and where it's undefined. Now, because it's twice differentiable, I know that the derivative exists, and if I look at this, that's defined everywhere, right? Because it's just a continuous function multiplied by another continuous function. So the only thing I have to worry about is just when the derivative is equal to 0. So I'll apply the zero product property. And set each of the factors equal to 0. So one solution is 19 over 7. Now, before I continue, I need to make sure that this is also in the domain of my function. Is 19 over 7 on the interval from 1 to 4? Yes, right? 19 over 7 is less than 3. Okay, and now let's do this one. So we'll do sine inverse of both sides. What's sine inverse of 0? Should be able to do this without any hesitation. So we could have sine is the y coordinate, right? So sine is equal to 0 at 0 and at pi. So far, so good. So if I set this equal to 0, I get that x equals 2. So that one should be good. If I set this one equal to pi, was this a calculator active problem? Okay, good. It was. This we have to use the quadratic formula for, right? Actually, we don't. Never mind. Let's just do it the same way we did before. You can do that. Square root both sides. So I can say that. Now, 2 minus the square root of pi, I suspect is going to be less than 1 and not be applicable for us. Yeah. And then 2 plus the square root of pi. Oof. I don't think that's going to be bigger than 4. But let's check. Oops. Nope. So what are my critical points? I have 3 of them, right? I have 2, and then the 19 over 7. Is that bigger than that or smaller than that? I think it's probably smaller. Oh yeah, of course it is, you dumbo. It's less than 3. So far, so good. Okay, and now I'm going to pick some test values. So I don't want to use 1 because if I look at, well, I guess I could use 1. That's all right. Let's use 1 then. And then this will be like 2.5, and then maybe 3, and then we'll do 4. Those be our test values. Everybody's okay with that? When I plug these in, so I want to do this without a calculator. Yeah, it'll probably be all right. When I plug 1 in, I get negative here. I'm going to think about this as x minus 2 squared, right? Everybody's okay there? I know sine is positive from 0 to pi, right? So anything that's less than pi and I do sine of, I know it's going to be positive. When I plug 1 in there, that just gives me 1 squared, or negative 1 squared, or 1. Sine of 1 should be positive. So that should be negative. Because I have a negative times a positive. Should I write it like that way? So I plugged into here, I get a negative. I plug in here, I get positive. Now there's a calculator active problem. You could just type it into your calculator, right, if you wanted to. But you could do this problem even if it wasn't calculator active, I suspect. Although you have to use a little bit of intuition about like what's in between, which is kind of stinky. I plug in 2.5, and 7 times 2.5 is like 17.5, so that's still going to be negative. I do 2.5 minus 2 is a half, and a half squared is a fourth, and sine of a fourth should be positive. So that section is negative. So 2 is neither a local minimum nor a maximum. If I do 3, 7 times 3 is 21, so minus 19 is positive. If I do 3 minus 2, I get 1. 1 squared is still 1. Sine of 1 should be positive. So that section is positive. And if I do 4, 7 times 4 is 21, minus 19 is positive. 4 minus 2 is 2. 2 squared is 4. Sine of 4, though, that's bigger than pi, so that should be negative. So my critical values were at x equals 19 over, let's write them in order, dum-dum, 2, 19 over 7, and 2 plus that. And I found that x equals 2 is neither min nor max, because f prime of x is less than 0 on the interval from 1 to 2, and f prime of x is less than 0 on the interval from 2 to 19 over 7. X equals 19 over 7 is a, we're going decreasing to increasing, so that's a local minimum, because f prime of x is less than 0 on the interval from 2 to 19 over 7, and f prime of x is greater than 0 on the interval from 19 over 7 to 2 plus root pi. And then we said x equals 2 plus root pi is a local maximum, because we go from increasing to decreasing, because f prime of x is greater than 0 on that interval from 19 over 7 to 2 plus pi, and it's negative on the interval from 2 plus root pi to 4. That was a lot. Now again, you could have done this graphically, right? Since it had a calculator, you could have just typed in the first derivative, found the zeros, and looked at what the graph was happening before and after. I did it all algebraically so that you can see that method too, because like using your calculator, it's obvious, I hope, right? You just type in the derivative, find the zeros with the calculator doing the zero command. Just look at if it's positive or negative before the zeros, and not much to do. So it could have been quick. Says use the line tangent to the graph at x equals 1.5 to approximate f of 1.8. Okay? So we have a point, because we know that f of 1.5 is equal to 3. And we know we have a slope, because we know m is going to equal f prime of 1.5. So if I plug in 1.5 there, I'm just going to use my calculator at this point. I yield, so what do we have, 7 x minus 19, and then sine of, I'm just going to write it as x minus 2 squared because it's just less typing. So I'm going to evaluate that at 1.5. So negative 2.1. So we have y minus 3 equals negative 1.2 times x minus 1.5. And if I plug 1.8 into that, f of, just double check that I did that right. Yeah, okay, f of. So I just do that, right? So that's about 2.6 or 2.37. And then I assume these are supposed to be C and D. On the interval from 1.5 to 1.8, f prime of x is less than 0 and f double prime is greater than 0. Is the approximation found in part B an overestimate or underestimate? Give the reason for your answer. So since it's f prime of x is, was that negative or positive? I forget now. Negative, f is decreasing, and f prime of x is positive. That means f is concave up. So I want to make something that's, draw something that's decreasing and concave up. So that tangent line is going to be an underestimate, right? Because this is like f of 1.8, and this would be like our approximation. All right. So I just kind of used a picture there. It says, using the mean value theorem, explain why the average rate of change over the interval 1.4 cannot equal 6.5. What was it? 1 to 4? Is that what this interval was? Yeah. So since it's twice differentiable by the mean value theorem, we know there exists a C on that interval such that f prime of C equals f of 4 minus f of 1 divided by 4 minus 1. Well, let's see. Let's just say AB here, actually. And I'll change those to BA and then B minus A. And I'll add in here subset of 1, 4. So what I'm going to do is I'm going to assume that f of b minus f of a over b minus a equals 6.5. So I should be able to find something where f prime equals 6.5. So I know that should have a solution by the mean value theorem, right? Let's try to find it. And then it was sine this. What's going to be the best way to solve that? Calculator. Am I going too fast? Is this okay?
No.
Okay. Yeah, if I'm doing anything you don't like, please like holler at me to stop. And then we got to go from 1 to 4. And then I got to go at least up to 6.5. I'll just go to 10 or something. That should be enough. So I can see from the graph that this has no solution. Right, so you could do something like that, and that's probably okay. What would be better, though, is to show that the maximum value of f prime is less than 6.5, right? So to do that, I'm going to look at the second derivative. So I'm just basically going to do the first derivative test on the second derivative, which is kind of weird to think about. So derivative sine is cosine. Oops, it's minus. So I set that equal to 0. And I'm going to solve that with my calculator. Now, this method that we're doing right here is going to be slower than what I just did. But why I said it's better is because it's like more rigorous, would be my argument. Like you're using more calculus to do this, which as an AP grader, I think you'd be excited to see, be like, yeah, that's a better approach. Of course, yes. Okay. Ooh, a lot of stuff to type in. So here I can see that I have a local minimum at this value because we're going from decreasing to increasing. And I have a local maximum at this value where we're going from increasing to decreasing. I'm sorry, from increasing to decreasing. So this is really the one that I care about. So let's find those values. So 2. And the next one. Bloop. 3.28. So we know that this is a local minimum because f double prime is less than 0 on 1 to 2. And it's greater than 0 on 2 to 3.28. And this is a local maximum because second derivative is greater than 0 on 2 to 3.28, and it's less than 0 on 3.28 to 4. And then if I do f prime of 3.28, that's less than 6.5. So clearly this has no solution, right? That's my contradiction. So either approach I think is fine. I think you'd get full marks on either approach from an AP person. I think the second approach is a little bit more rigorous because you're using like calculus tools to do it rather than just saying like, yeah, there's no solution to that because look, I graphed it and there's no intersection, which I think is probably fine because it's a calculator active problem. This I used a lot more calculus to do, which I think they'd probably like better, but I'm just speculating at this point. I would count both of them correct for the same amount of correctness. Sure. Probably have time for 1 or 2 more, depending on how long the questions are. Christian. Sure, tiny it away.
What is the ln of 0?
Negative infinity. If you're talking about the limit as x approaches 0 from the right of the natural log of x, negative infinity. Because if I graph the natural log of x, that's what it looks like. Correct. That I think is still infinity. Yeah, let's double check here. Yeah, it's not indeterminate. Those are the 7 indeterminate forms. That's it. Okay, those were tiny questions. Tiny questions in the class. Others. Those were tiny. We still have time for more. if you'd like to talk about more. Any multiple choice stuff? Any other homework questions? Whatevers? Giselle, is that a hand, or is that you're just contemplating?
Yeah.
Okay.
No, I'm good.
Okay. Okay. Well, let's do 4-5 then. So the goal in section 4-5 is going to be to provide an accurate sketch of our graph by hand, assuming that we have no functioning calculator. This was something when Mr. Kulik was a student your age that we were asked to do routinely because the graphing calculator was not widely available. It's a fun time to be alive. You guys are so lucky. So for us to graph, we're going to be worried about representing these 7 features. So I'm going to worry about finding the domain because I need to know where the discontinuities are. If I'm going to draw a graph, an accurate graph, I definitely need to know what those are or where those are. I'm going to want to include the intercepts, both x-intercepts and y-intercepts, so where the graph crosses the x-axis and the y-axis. I'm going to be interested in any kind of symmetry, whether it's even, odd, or periodic, because that is going to save me a heck of a lot of work if I have something that's odd or even, because I can just copy the other half of it. Or periodic means I just need one period of it, and I can just keep repeating. I want to include any asymptotes, horizontal, vertical, or slant. And then I want to know where the graph is increasing and decreasing. It's their local mins and maxes, and then concavity and inflection points. So if I think about it, like these skills are kind of like Algebra 2 skills, and these skills are like our calculus skills, right? Notice that we overlap a little bit at the asymptotes point. Oftentimes we'll use our Algebra 2 rules for asymptotes as opposed to the calculus rules for asymptotes, because most of us probably don't want to deal with the limits to get the asymptotes. Everybody okay? We're probably just going to do 1 or 2 of these examples because, well, as you might guess by looking at them, it's a little involved, right? So I have a whole bunch of ones to choose from. What do you want to do? Maybe just the first one or something? So if I look at the first one, what type of function is this? You should recognize this from your Algebra 2 class. What do we call this kind of function? We'd call it a rational function because it's the quotient of 2 polynomials, right? Polynomial divided by polynomial is called a rational function. How do we find the domain of a rational function? Not where the top is 0, the bottom is 0. So we know that the bottom cannot equal 0. So plus or minus 1. So my domain would be -1, or negative infinity to -1, union -1 to 1, union 1 to positive infinity. Feel good so far? Okay. So let's do y-intercept first. How do we find the y-intercept? Nope. Yeah, plug in 0 for x. So we get 0 there, right? So that's the point, 0 for x, and then 0 for y. Hey, what do you also notice about that point? Oh, guys. Yes, it's yours. It's also an x-intercept, right? Because the y-coordinate is 0 also. So this is an x and a y-intercept. It's both. Everybody's okay there? Now, Christian, how do I find the x-intercepts? When the numerator is 0, right? A fraction can equal 0 only when the numerator is 0. Well, clearly that's just 0, 0 again. So our x-intercept, our only x-intercept is also the y-intercept. Everybody's good there? Oops. So next we'll look at odd, even, or neither. So remember, to tell the difference between odd and even, we're going to do f of negative x and see what we get. Hey, what do you notice? It's the same, right? So it's even. Now, what does that tell me about the graph? It's that it's a mere reflection across the y-axis, right? That's what even is telling me, which is lovely because now I only have to really worry about 1/2 of it. I don't have to worry about the other half. Yeah, dude. All right. Asymptotes. How do I find a vertical asymptote for a rational function? Remember that a vertical asymptote is a type of discontinuity, right? It's when the bottom is 0. How do I find the horizontal or slant asymptotes for a rational function? Remember, there's 3 sets of rules on how to do this. Yeah, you're comparing the degrees of the numerator and denominator. In this case, the degrees are equal, which tells us that we have a horizontal asymptote at not at 0 and not at 1, not at -1. It's the leading coefficient of the numerator over the leading coefficient of the denominator. And we have no slant. When would we have a slant? If the degree of the numerator is bigger than the degree of the denominator. What happens if they're less than? And it's a horizontal at y equals 0. Good, Katie. Everybody okay there? Again, we could have done that part with calculus and limits, but like, We know these rules already. We're probably more familiar with that and feel more comfortable with that than the limits. So far, so good? So I'm going to do increasing, decreasing, and max and min all together because I'm just going to do a first derivative test to do this, and I need, if I'm doing a first derivative test, I get all those parts all at once. Okay. So if I do, well, let's maybe call it y prime. I think they called it y in the beginning. So here we have the bottom times the derivative of the top minus the top times derivative of the bottom all over the bottom squared. Does that all look okay? Did I make any mistake there? Right? I think I did that all good. Okay. So when I simplify this down, what do we get? Just that, right? What are my critical values going to be for that? When's it equal to 0? So at 0. Or when it's undefined, right? Where is it undefined? 1 or negative 1. But do those actually count? What is f undefined at? We just did it a second ago. The vertical asymptote, so 1 and negative 1. So do those count as critical values? No, they do not. Everybody's okay? So we have just the one critical value. Now notice that the denominator is always positive because it's something squared. So all I'm really checking is if I plug negative 2 into the top, do I get something positive or negative? So negative 4 times negative 2 is positive. So the derivative there is positive. So we're increasing. And then when I plug 2 in, I get negative. So we're decreasing. So if we're going from increasing to decreasing, we know that x equals 0 is a local maximum, i.e. 0, 0 is my local max. So far, so good. All right, last part. Going to find the intervals of concave up and concave down and inflection points. To do this, I need the second derivative. So I'm going to take the bottom times the derivative of the top minus the top times derivative of the bottom all over the bottom squared. Is everybody okay with what I did there? I'm now going to factor the numerator. You could multiply it out, but I find it usually easier to plug stuff in if it's in a factored form. So if I look at these two terms, this is one term, this is my other term. What's in common to both of them? A -4. Everybody agree with that? And an x squared minus 1. Everybody agree? After I factor those out of the yellow, what's left? Okay. And then I still have the subtraction symbol. And what's left in the blue? 4x. Okay. Well, we can do this. Well, 4x squared. Yes, thank you. Very good, Brooke. Thank you, thank you, thank you. So that is going to be -3x squared minus 1. So I'm still going to do that reducing with the x squared minus 1s. Everybody's okay there? All right. So I'm going to set the second derivative equal to 0. So that just really implies -3x squared minus 1 is equal to 0. So I get x equals plus or minus the square root of 1 over 3. You guys agree with that? Oh, wait a minute. Hold on. What? I'm sorry. Okay, go. You go.
Why was it only like the negative x squared minus 1 equals 0, not the entire function?
Well, I only have to worry about where the numerator is 0. And the only thing left up there is the -4.
Oh.
So I don't care about that because I reduced the other piece out.
Got it.
Right? We're doing okay?
Yeah.
Okay. Yeah, no. Nope. Okay. And if I set that equal to 0, though, I'm getting undefined, right? What happened here? Made some kind of dumb mistake. Who sees it? Okay. So we have no, everything is fine. So this has no solution. I'm good. Right? That's all fine. However, I don't have any candidates for inflection points. but the graph can still change concavity. Where can this graph still change concavity even though it has no inflection points? Yes, at the undefined parts. Very good. So when I'm figuring out my intervals of concavity, I still have to worry about my undefined parts, even though I don't have any inflection points. So if I plug -1 in, I'm sorry, -2 in, goodness gracious, I was like, what's going on? No. All right. The numerator is going to be positive, right? Because I'm going to have a negative times a negative. And the denominator is going to be positive also. When I plug 0 in, I'm going to have a negative times a negative in the numerator, -4 times -1, and I'm going to have a negative in the denominator. So that should be negative. And when I plug a 2 in, it's going to be the same thing as -2, right? Because all the x's are just squared, so like, not surprising. So we're concave up on those intervals, and we're concave down on that one. Katie. So, but all the x's are squared, right? So I'm plugging it in here, and I'm going to have a -4 times a negative something. Right? And this whole thing has to be negative. And this down here will be positive. So I have 2 negatives divided by a positive is positive. Yeah, no problem. Again, it's tough to see that there's like a lot of stuff going on. I didn't leave myself enough space and it got kind of all squished in there. All right. Should we start drawing ourselves a picture now? We got all collected all of our pieces together. So here I got some vertical asymptotes, I got some horizontal asymptote. I don't care a lick about the scale. You could be a little bit more accurate than I'm being. Clearly, this is not well scaled because 1 looks like twice as big as 2. That seems weird. Should we fix that? Maybe we should. That's just sloppy. I guess it would have made more sense to just make 2 taller. That's better. So we know that we are between -1 and +1, we're concave down, and 0, 0 is my maximum. So it's got to look something like that, right? From -infinity to -1, we're concave up and we're increasing. So it's got to look like that. From +1 to infinity, we're concave up, but we're decreasing. So it's got to look like that. And if I look at this picture, this is a reflection across the y-axis of each other. So I think this fits everything we observed analytically. Everybody feel pretty good about what we did here? No new ideas, right? This is all just like putting together a bunch of skills that we've had to do like this one graphing thing. Do you want to do another one? It's okay if you don't. You just be like, I'm cooked. I get it. The homework for this section is 6 problems, which is kind of bad, right? Like that's cool. Like that took forever to do one. The good news is that like 61 and 63 are just asking you for like, they don't actually want you to sketch it. They just ask you to do like one thing. So it's like 4 problems really, because the last 2 are just like, just do a little part of this process. And it's like, okay, well that now sounds a lot nicer. And the first one's real easy because it's just like a quadratic. So, you know. No! No! No, let's do this Sunday.
4, 3, 4, 4.
Yeah, 4, 3, and 4, 4. That sounds good. We got some more time if you guys want to do some more questions from stuffs. Or if you just want to sit and chat and hang out. Okay. I'm going to stop the recording. Cool.